Welcome back to algorithms. So today we're going to go in depth on the master theorem. So we'll separate out the different cases and see what they mean kind of specifically, and interpret the role that A, B, and the overhead term play in the different cases. We'll also prove the master theorem. At least we'll give a sketch of the proof of the master theorem. And then we'll see our first major kind of significant application of divide and conquer in the merge sort algorithm, which apparently Microsoft believes is not a word. All right, so the master theorem goes like this. Let me quickly reintroduce the master theorem. Of course, for the depths of this, you can go back to the previous video. So the master theorem says something about the divide and conquer recurrence relation, which is given by this. It says T of n is A times T of n over B plus some overhead term f of n. And here we have our requirements that A is greater than or equal to 1, and B is greater than 1. Notice B has to be greater than 1, because if it isn't, then this recursion will never terminate, right? It's recursing on, if B were, say, equal to 1, this recursion would be recursing on just the same size input every single time. The input would never shrink, so we would never be able to approach some base case. So we're going to define the critical exponent using this letter C as the log base B of A. And so that's just looking at the terms in the recursion, right? In the recursive piece of this, right? It doesn't capture anything about the f of n. And then to figure out what the master theorem tells us, right? To differentiate the cases, we're going to compare f of n to a polynomial of degree c. Okay, so we're going to compare f of n to an n to the c polynomial function. So I'm going to call case 1 the overhead dominant case. So this is my f of n dominates. And I'll try to be consistent and with my case numbering, right? So we'll try to be consistent and say this is case 1. So f of n dominates. So what does it mean for f of n to dominate? It means that if I were to plot this critical exponent, so if I were to plot the function n to the c, then in an asymptotic sense, f of n is strictly up here. Okay? And when I say strictly, I mean it in the following sense. I mean that f of n can be shown to be big omega of some polynomial that has a degree strictly higher than c. Okay, so f of n is big omega of n to the d with d greater than c. Right? So this is a little nitpicky. This is a way of saying that this is a way of defining a notion of strictness in my inequality, or in my asymptotic inequality. But that's what we're doing here. And read this as f of n grows strictly faster, right? Is strictly worse than n to the c. You know, if I had two algorithms running beside each other, one of them is f of n, has f of n complexity, and one of them has an n to the c complexity. N to the c would finish faster, essentially, right? It's asymptotically is more scalable than f of n. So if f of n dominates, then what do we have? Well, then we have this really easy result that says if f of n is the biggest part, then f of n runs the show, right? Then T of n, right, my overall recurrence relation, has the same complexity class as f of n, right? So big theta of f of n. Okay, so that's case 1. If f of n is big, then T of n just inherits f of n's complexity. Done. All right, so now what's my case 2? So I'll call case 2 the balanced case. So here in case 2, the notion is the f of n is just exactly right, that it sort of balances out the recursion. And so in the balanced case, we had this is the special one. This is the one that isn't is the least obvious in some ways. But in this one, we'll call this balanced. And what are we looking for with this one? Well, we're looking for if we were to plot this n to the c, then our f of n would exactly match it, right? F of n would follow right along, right? And so what we're saying, and with up to a log slowdown, right? So we have first we're sort of saying f of n is polynomial with degree c, but then also could have some log slowdowns, right? It could have k log slowdowns. So here's the formal way of writing this. So let's say if f of n is in big theta of n to the c, with up to k log slowdowns, right? Times log n raised to the k power. So we're multiplying on k log slowdowns. And so, you could say, maybe a log slowdown just puts us a tiny bit above, but only a tiny bit, all right? No more than log above. Okay, so if we're in this case, then what do we get? Well, we get the following. We get this fact that then t of n is f of n times a log slowdown. Okay, so if f of n is n to the c with k logs, then t of n is f of n times one more log. Okay, and so we can write that, rather than referencing f of n, we can write that like this. We can say t of n is big theta of n to the c log n now to the k plus 1 power. Okay, and so the interpretation here is that if we're in the balanced case, then t of n looks just like f of n with a log slowdown, right? So t of n looks like f of n with a log slowdown. Okay, so that's the balanced case. All right, and then case 3 looks like this. So case 3 is the one where the recursion dominates. And so last time we drew these recursion trees, and we derived the number of leaves that are in the recursion tree, and that corresponds to the number of base case executions that you get in the recursion. So in case 3, we have the recursion dominates. And here, what do we say? Well, if we were to plot out these functions, and we plot, here's n to the c, what the recursion dominates means that f of n is somewhere down here. So f of n is strictly slow, it grows strictly more slowly, or the overhead term runs strictly faster than a function or an algorithm with complexity n to the c. So here what we say is f of n is big O, so it's dominated by some polynomial where now d is less than c. So if I were to draw this on the picture, what this would look like is there's some other polynomial here that has a strictly lower degree than c, right? Some n to the d, and f of n is big O of that. Okay, so that's the picture. So in this case, what do we get? Well, we get that the overall t of n, then t of n adopts the complexity that's governed by the number of times the base case gets executed in the recursion. Which is to say, we have to do some graph theoretic stuff and think about how many leaves are there in a tree that has a branches and log b levels and things like this. But we have the following: t of n is big theta of n to the c. Okay, which is to say big theta of n to the log base b of a. So big theta of n to the log base b of a. Okay, so those are our cases. Those are the main cases of the master theorem. So now let's think a little bit in the next video about what this means. Right? What does this tell us about the algorithm design process, if indeed it tells us anything?